Good morning, everyone. Thank you for joining our data science series. Today, our pleasure to have Dr. Arunesh Sinha from School of Computing and Information System, Singapore Management University. So Dr. Sinha got his Ph.D. from CMU in 2014. And his research mainly is on AI, from game theory to machine learning, and address a lot of problems in adversarial reasoning with applications in real world application in real world. With a lot of publications in top tier venues, something like AAAI, EGKI, AMAS, and a number of big grant funding. So I'm now the podium is yours, and enlightening us with your exciting research. Thank you.
Okay, thanks a lot for that introduction. So today I'm going to talk about AI, and specifically this topic in AI of multi-agent systems and how that can be used for the benefit of society. So my work is inspired by problems in the real world, such as physical safety problems, as well as safety problems that arise in the cyber world. Another topic of great interest and motivation for me is the problem where AI fails. And this, we know, is a problem if people from Google Brain come out with memes like this. But on a more serious note, there are industry-wide studies which show that there are many problems that plague the adoption of AI in the real world. And security and privacy, as well as data quality, are some of the primary reasons. And I'm going to focus on data or simulation quality in my talk. So in response to these motivating topics, my work has focused on game theory and learning for security. And another more recent thrust has been on high fidelity simulation of complex human decision-making systems. So in the part on game theory, my work has mostly looked at this area of Stackelberg security games. This was already quite a successful area even before I started my PhD. This has found applications in the real world. It's used to allocate air marshals on flights and patrol ports on the US ports. But modern problems are more complex. They are larger game models. So these prior methods that were used to solve these old kind of applications do not scale up to today's scale or complexity. So that's what I focus on in this work. In learning on games, if there is data available about the opponent behavior, then instead of assuming a rational opponent, we can actually learn the behavior of the opponent. And with that learned behavior, then we can optimize the defender's strategy. Now, this learning within games is hard because provable guarantees are kind of rare in this area, as well as robustness to learning mistakes is also really hard. So this is what some of my work focuses on in this area. And the most recent thrust that I am also very interested in is data-driven simulation, especially of these kind of complex systems where there is human decision-making involved, such as transportation or even computer networks where humans are interacting with the network. Now, classic simulation in AI uses this agent-based models, agent-based simulation. These are very stylized models and are therefore not considered very realistic. So can we harness the power of data as well as neural networks to build more realistic simulations given such ample data that is available from such complex systems? Now, my contribution in these topics, again on games, in my PhD, I introduced this area of audit games, the application of which was auditing for privacy violations. In my postdoc, I introduced this topic of threat screening games, the application of which was screening of airport passengers. This was actually tested at a few airports in the US. And then I've continued that line of work investigating more recently on topics of deception, where if you're learning about adversary behavior, the adversary could deceive you by playing suboptimally. Continuing that line of learning and games, I have worked on applications in urban and wildlife crime prevention, as well as done more theoretical and basic research in formal analysis of trying to come up with formal guarantees of what does learning within games mean. The purpose of which, of course, to make AI more robust. And in this thrust on higher fidelity simulation, I started off this problem with a paper on modeling stock market orders that come into the market. And the long-term goal of that is to design reinforcement learning strategies for traders in stock markets. I have used similar kind of techniques for maritime traffic modeling in Singapore, as well as a more recent basic fundamental theoretical kind of research on low and biased data. If there is such low and biased data present, can we still learn some fine-grained simulation model for large-scale systems? My work also has a real-world impact. As I said, one of the threat screening game problems was tested in airports in USA, as well as there is some work which I'm not going to talk about in detail today, but I'm doing with Google Research in India, which is part of their AI for social good effort, where I'm working with actually an NGO in India on the ground. This is very much on the ground real-world work. These are my publications. I have already listed the ones in green here. There are a few other publications at the bottom that I have listed on topics of adversarial learning, as well as general game algorithms, as well as some bandit algorithms. Of course, in this talk, I cannot talk about all of them. I'm going to focus on a few of them. So I'm going to focus on two papers in threat screening games, as well as I'm going to talk about our more recent work on simulation, and then end with a broad vision of where I'm trying to take all of this work in future. So to get started with threat screening game, I'll first introduce the concept of Stackelberg security game, because threat screening game builds upon this concept. So in such a game, there is a defender and an adversary. In this game, in this small toy example here, the defender wants to defend one of these two flights. He can only defend one of them, and the adversary wants to attack one of these two flights. If the defender and the adversary choose the same flight, suppose this blue one, then the adversary loses. The adversary gets a payoff of 0 and the defender gets a payoff of 1. If the defender chooses the white flight while the adversary chooses the blue one, the adversary wins. His attack works. He gets a positive payoff of 9 and the defender gets a negative payoff of -9. Now, in this game, if the defender, suppose, defends the same flight every day, then it's obvious what the adversary should do. He should attack that other flight which is not defended. So deterministic strategies are bad in such games. What is better is randomized strategy. If the adversary were to randomize his defense, then if the defender were to randomize his defense, the adversary cannot predict which flight will be protected the next day. So this is the concept of Stackelberg security game, where a defender first lays out his defense. The adversary knows about the defender's randomization. He does not know the exact coin flip on any day, so he doesn't know which flight will be protected. And the Stackelberg equilibrium concept that is arising out of the Stackelberg game is to compute this optimal randomization, these probabilities with which these actions should be played by the defender. Now, before moving on, I also want to give a pictorial view of the optimization which is used to compute the Stackelberg equilibrium, because I will return to this later in the presentation. So in here, we can specify the pure strategy or the actions available to the defender as these vectors, 1 and 0. 1 means that flight is protected, 0 means the flight is not protected. So there are 3 possibilities here, including a naive one where none of the flights are protected. So because this is just 2 options, we can plot them out on this 2-dimensional plane, as I have done here. And the defender, if he has to randomize over these actions, then then we can view these axes as probabilities of defending flight 1 and flight 2. And then the mixed strategy, which is just a randomization over the pure strategies, is nothing but the convex combination of these pure strategies, which is all these blue points here, shaded in blue, are valid mixed strategies. So this forms the optimization space for the defender, the feasible space. What does the adversary's response do? So the adversary's best response actually divides this space into two parts, one of which the adversary finds it better to attack flight 1, and the other one he finds it better to attack flight 2. And if we solve for the optimal randomization here, we might end up with this cross here, which is like the optimal point. So this is a very brief overview of how the optimization in a Stackelberg game looks like. At a high level, all of this Stackelberg security game is randomized allocation of limited security resources in an adversarial setting. So now coming to threat screening games, these are the largest example of Stackelberg security games. So this problem is one which was done in collaboration with TSA. The problem here is that TSA wants an effective balance between screening effectiveness as well as timely screening, meaning there are some screening resources that are good but take a lot of time to screen. We cannot use that for every passenger, otherwise the queues will build up too long. So we need this balance here. So who are the players in this game? So in this game, there's a defender, the TSA, and an adversary, the terrorist, and there are many benign passengers. Now, let me talk about the problem briefly. So the problem is that the passengers come in and the defender has to detect this adversary who's here. Of course, the defender does not see the adversary like that. Otherwise, the problem is trivial. The defender sees every passenger as the same. Okay. In order to detect the adversary, the defender has these screening resources, as an example, 3 of these. And maybe there's some screening resources that are effective. They will detect the adversary, but they are slow. So they will build up large queues if every passenger has to go through this screening resource. So that's the problem. How do we address this? So even before going into the technical details, I'll just state out our proposed solution. Okay. So our proposed solution is that we divide the passengers into passenger categories. For example, I'm just showing 4 categories here. High risk taking flight 1, high risk taking flight 2, low risk flight 1, low risk flight 2. And as a passenger comes in, so suppose this one is low risk taking flight 2, he goes to an allocated lane for low risk flight 2, which in turn maps to a probability of going through each of these screening resources. So then there will be some coin flips and this passenger might go through the metal detector. So the next passenger comes in, low risk taking flight 1, he goes to his own specific lane with a different probability distribution of seeing these different resources. Again, there might be some coin flips and this passenger also goes through metal detector. Finally, another passenger comes in, high risk taking flight 1, which maps to yet another probability distribution. Now you can see that there is more weight on the X-ray plus metal detector, which is the more effective screening resource. So very likely this high risk passenger might go through the X-ray and metal detector screen. So this is how our proposed solution would work in practice. What were the technical challenges in doing this? So as I said already, this is the largest instance of Stackelberg security games. The equilibrium computation here is NP-hard. We can show that. Current operation research methods, such as column generation, fail to scale up here. And I'll show a comparison. And if we do some sort of a compact representation, that could result in invalid solutions. So our contribution is we propose an algorithm called the marginal guided algorithm, MGA in short, which ensures that the solution is always valid. It identifies the conditions under which it is optimal. And even when those conditions are not met, we have strong evidence of optimality. So here I'm comparing MGA with the baseline of column generation, which is like a OR method. And as you can see, the runtimes of MGA are much better for different problem sizes on the x-axis. Different problem sizes correspond to different number of flights per hour. And the solution quality, so the higher is better here, is of MGA is also better than column generation, even though it takes much less time. So that's showing that MGA is much more effective than our best baseline of column generation. Okay, so with that overview, I'm now going to go into a little more technical details on how we solve the problem. So since this is a Stackelberg security game, the pure action of the defender will be some sort of an integer allocation. So how do we get that? We divide the time into time windows, time window of 1 hour each. And in each hour, we know the estimated number of passengers coming in for every passenger category. That's those numbers written in the brackets at the top, 10, 5, 50, and 20. This is the number of passengers for every passenger category in an hour, as an example. Okay. And then we have to allocate these passengers to these different screening resources shown on the rows. Okay. So one natural constraint for such an allocation should be that whoever comes in should be screened. So the sum of every column should be equal to that number on the top. As you can see, that is true in this particular allocation I'm showing here. That's not the only possible allocation. We can put integers at different places also. But whatever numbers we put in here, whatever integers, they should satisfy this flow constraint. There's yet another type of constraint they should satisfy, which is the resource capacity constraint. So for example, the X-ray can only be used 50 times in an hour. And X-ray is being used for all the passengers in this first 2 rows. So the first 2 rows must sum up to less than 50. And there will be an analogous constraint for the metal detector, which is on the bottom 2 rows. These must sum up to less than 60 if the metal detector can be used 60 times in an hour. So any such matrix with integer entries that satisfy the flow constraint and the capacity constraint is a valid defender pure strategy. What is the adversary's pure strategy there? I'm simplifying things here a little bit from the paper, but the adversary's pure strategy is just to choose a column, the flight to take as well as a risk category. Okay, now what is the problem here? The problem here is the number of pure strategies of the defender is exponential. It's huge because this is all those integer matrices that satisfy the flow and the capacity constraint. That's a very large number. And the mixed strategy of the defender is a probability distribution over pure strategies, which we can represent using these variables P1, P2 to Pn. Okay, but there are many of these. Now, with these variables, we can also define the convex combination of these pure strategies. So where this convex combination is weighted by these probabilities, that gives an expected allocation matrix, which I'm writing as this n here. So this in this matrix, expected allocation matrix, the numbers can be real numbers. They do not have to be integers. Now, given such an expected allocation matrix, the defender's utility, and given an adversary action, which is, say, high-risk flight 1, the defender's utility can be written as a linear function in the entries of this matrix, this expected allocation matrix, in these n's. I'm not writing out the exact function here because that's kind of complicated, but the only thing that's important is that it's linear. Once we have this, we can write out an optimization problem. So this is the classic Stackelberg equilibrium optimization problem, which is to maximize the defender's utility. That's what's the objective here. Subject to the constraint, the first constraint here is saying that this n must be a valid defender strategy, which is given as a convex combination of the pure strategies. And this second constraint is saying that the adversary plays a best response. So in response to n, the adversary chooses an action that is best for the adversary. So AU here is the adversary utility. So that gives the best response A star, and that is what is used in the objective. Now, if we make this a zero-sum game, so the adversary's utility is negation of the defender's utility, and if we do that, then this whole optimization can be converted into a linear program with additional variables. But even though it's a linear program, it's actually exponentially large in the input size. And because of that, we can show that the equilibrium computation is NP hard. So how do we address this problem? First, let's look at what we can do with something called a compact representation. So right now, the way I'm representing the defender strategy is a convex combination of the pure strategies. So if you think of these pure strategies as some integer points in some high dimension space, I'm drawing here only on 2 dimensions because I cannot draw high dimension. So in 2 dimension space, all these dots are like some integer points in a high dimension space. Then the defender's mixed strategy is a convex combination of these pure strategies, which is nothing but any valid defender mixed strategy will be the convex hull of these pure strategies. So that's one thing. As I showed earlier, the adversary's best response essentially divides the space of the defender's mixed strategy into 2 parts, or in general into n parts. So it is difficult to optimize over such an object, okay, which is a convex combination of exponentially many integer points. What can be done as an alternative is to have a compact representation where we directly impose the flow and the capacity constraints on the matrix n, the real value matrix itself. And we keep the adversary best response as is. The issue with this compact representation is that the feasible space that it results in is this dashed polytope, which happens to be actually larger than your valid mixed strategy space. So if we optimize with this dashed polytope, then we might end up with a solution, which is this red cross here. That's an invalid solution because that doesn't lie in the space of valid mixed strategies. So in the past, people have tried to solve this with an approach called incremental cut generation, which is essentially either column generation or something called constraint generation. The way it works is we use the compact representation, get the invalid solution, and then generate a cut, which is this dash line, to separate the invalid solution from the valid space of valid mixed strategy. And then we resolve the problem. We add this cut back to the compact constraints, resolve the problem, and hopefully we'll get a solution that's closer to the valid mixed strategy, which is on the cut here directly. Okay, but this still is not a valid solution. So we might have to generate many cuts, and there is one linear program to be solved every cut. And if we do that, then ultimately we will achieve this solution in the green one. But it will require many iterations and many linear programs to be solved. That is what makes this slow. We do this somewhat differently. We again use the compact representation, get the invalid solution. That is how we start with. But then what we do is we try to reconstruct the relevant part of this valid polytope from inside. So how do we do that? We construct a subpolyhedron with one vertex near the invalid solution, okay, but there are more vertices that could be near the invalid solution. So we construct yet more subpolyhedrons like this green one. And once we have generated enough subpolyhedrons, we can take the convex hull of the subpolyhedrons, which can be done as a linear constraint. So that's good. So our whole constraint set is still linear. And once we have done that, then we have reconstructed the part of the polytope that's near the invalid solution. That is what this black polytope is. And now we bring back our adversary best response and solve just with the black polytope. We will recover this solution, the green one. Okay. So what we can show that the solution that we get is always valid. And we can also show that it is optimal if we have to only construct one subpolyhedron. Okay. And as I had said earlier, even if we have to construct multiple subpolyhedron, we have strong empirical evidence of optimality. We never found an instance where it was not optimal. And our runtimes, of course, as I showed earlier, are much better than the baseline of column generation, as well as the screener's utility. The higher is better here is also much better than the baseline of the of column generation, even though our approach takes much less time. Okay, so that ends my part on the first paper on threat screening games. Now, there were a couple of papers in between, but I'll directly jump to this more recent paper from 2020, where what we got as feedback was in my earlier approach, what we did was we divided the time into time windows of 1 hour. And we said that, okay, anyone who comes in 1 hour must be screened in that hour. So we are treating delay here like a second class objective, because passenger arrivals is not like uniformly over the hour. Okay, they might arrive in bursts. So if they all arrive in the last 15 minutes, then we might not be able to screen all the passengers arriving in that hour. So this window-based approach doesn't really capture the delay nicely. So the feedback we got was that delay should be considered as a first-class objective. Okay, and we can do that. So the way we do that is we treat delay as a first-class objective and try to minimize delay directly. But we flip the problem around. Earlier, we were trying to maximize the defender's utility, or because it's zero-sum, it's minimizing the attacker's utility. Now, instead of minimizing the attacker's utility, we just put a constraint on the attacker's utility. We just say that it has to be lower than a certain value, and we will focus on minimizing the delay. So we flip the problem around, treat delay as a first-class objective, treat the security level as sort of a second-class objective. But that's if we do that, then actually we can cast this whole thing as a variation on a Markov decision process. I'm not going to go through that construction; it's tedious and long. But if we do this, make this a MDP, then we can use deep reinforcement learning methods. So a little bit about reinforcement learning or deep reinforcement learning. In reinforcement learning, you of course have a policy function which, given the state of the world, in our case, the state of the world would be what is the current queue length, and what is the category of the next passenger who's standing there to be screened. This should output the decision. The decision here is what is the probability distribution of where to send the next passenger to. Okay, so this is the output of this policy function. Of course, we are thinking of deep reinforcement learning here. So the policy function is replaced by a neural network. And there are very standard ways of training such deep reinforcement learning methods. Okay, so this is all good. As I said earlier, that we are putting some constraints on the expected attacker utility. The attacker utility is just a linear function of those probabilities that are output by the policy function. So if you want to bound the expected attacker utility, we have to impose some linear constraints on the probabilities that are output by the policy neural network. So pictorially, if this is the neural network, we want this output to lie inside this polytope with some linear constraints. Now, it by chance might lie inside, but it's very difficult to enforce the neural network's output to lie within some region. Okay, so it could produce points, these red points that are outside this polytope. So how do we address this problem? Now, there is also a vast approach which can actually address this problem. So let me first go through that. So suppose this is your neural network, it's outputting these points all over the place, not necessarily inside this polytope. The approach to solving this problem is to put another layer at the end, which is called a projection layer. So what does this projection layer do? What this projection layer does is that it projects these red points onto the polytope. So now they happen to be inside the polytope, all of them. And maybe the green one here is the optimal solution that we want, and we obtain that. So how do we do this projection? So this projection can be done by writing it as a quadratic optimization. Okay, so that's what's written here. So in the forward pass, there is actually a quadratic optimization that's solved to get these green and these black points here. Now, okay, so that's what's solved in the forward pass. What about the backward pass? So in the backward pass, we'll need to take a gradient through this optimization. Okay, now there are known methods of doing that. Okay, so that's not a contribution of this work, but there are earlier known methods of taking gradient through such convex optimization. So, okay, that can also be taken using that prior method. But what is the problem here? The problem here is that while training, we do this forward pass and backward pass millions of times, possibly. Okay, and what that means, in every forward pass, we have to solve this quadratic optimization. that makes the whole training process really, really slow. Because in every forward pass now we have to solve one big optimization. So how do we take care of such a costly process? Okay, we do that by proposing a different projection method. We call this pseudo projection because it's not mathematically a projection. It's the same setup as earlier. You have a neural network producing points. Now we have a different projection layer. We call it the alpha projection. How do we do this projection? We choose a center of this polytope and join that center with these red dots, and then choose those black points which are just on the boundary of the polytope along these lines. Okay. Now the good thing about such a construction is that you can actually write this out as a closed form formula. Okay, so it's very cheap. Okay, because writing it out as a closed form formula, evaluating a closed form formula is much cheaper than solving an optimization. The other part is because it's a closed form formula, we can also take the gradient through it very easy. Now you might ask, okay, what happened to this optimal solution here, the green one? Because this red one, if we had projected, it would have given the optimal solution. Now we are not getting it. So for that, we rely on the neural network. It's the neural network's responsibility to produce yet another red point here, which shows up as this light red here, such that if I join that light red point to the center and project it back, it would give me this optimal solution, this green dot here. And this one works much faster than the prior method that we had shown. And it also gets the optimal solution always. So the main point of that I want to claim from this threat screening games is that scalability is really critical for real world applications. And such novel optimization and approximation methods, as I showed earlier, are very much needed to make these things work in practice. Okay, so that ends my threat screening game part. Now I'll move on to the simulation part. So the real world is inherently multi-agent, meaning that there are many humans or many systems that interact with each other, such as in transportation networks or even computer networks. And if we can simulate these systems with high fidelity, realistic simulations, then those allow for making good policy decisions in such systems so as to get some optimal output out of these systems. And that's very critical in these days, especially like supply networks and all. If we can simulate nicely, then we can ensure that there's no failure in the supply network. So I'll show our simulation approach here with one example. I'll show the whole thing with just one example. Okay. So this example is one of a transportation network where there is a city that's divided into 3 districts. In each district, we look at the aggregate driver behavior of taxis. And we think of this as an agent, okay? So there are 3 agents here for 3 districts. Each agent is the aggregate driver behavior of taxis in that district. And these driver behaviors, the output of them, contribute to some aggregate city level behavior, which is, for example, the total supply of taxis in the city. Okay, so this is what we call as the mixer, the thing at the top. Now here I'm using this word agent. In AI, agent has a formal definition, but without going into formal definition, informally, an agent is something that senses the state of the world and outputs some action, which can be possibly randomized actions. So here, if you see, I'm showing the agent as a function. In our problem, the agent senses the traffic situation and outputs the driver's behavior. The driver's behavior here can be randomized. And because this agent is shown as a function, we can replace it with a neural network. Okay. The only issue with the neural network is if I directly replace it like this, then the output of the neural network is always deterministic. So in order to introduce randomization, we input some noise into the neural network, and that produces randomized actions. So this whole kind of thing is called a conditional generative model. So this is a conditional generator. It takes a noise as well as some condition of the world and then outputs the randomized action or decision. Now, this whole thing falls under the category of this generative adversarial networks. And there is a standard processes of standard way of training such networks. So if this is your conditional generator, it outputs these actions which have a particular distribution. We want this distribution of these actions to match the distribution of actions in the real world. So in order to do that matching, we during training only have this separate network, which is called either the critic or the discriminator, which is discarded after training. But this critic essentially provides a critic, meaning that it takes in this samples from the generated action. It also has access to the samples from the real world action. And then it estimates some sort of distance between the real and the generated distribution of actions. In particular, for one kind of GAN called the WGAN, it estimates what is called as the Wasserstein distance. And this estimate serves as a feedback to the generator, encouraging the generator to improve its distribution of action to match the real world distribution of actions. So that is how this training is done. After training, this discriminator is discarded, we only have the generator. Okay, so what am I thinking here? What I'm thinking is to replace every of these agents here with a conditional generator. That's what I have shown on the right side here. I have replaced every of the taxi behavior agent with a neural network. Even the mixer agent at the top is replaced with a conditional generator, where the conditions come from the output of these generators at the lower level. Okay. So this is showing how to do a multi-agent simulation. When there are multiple agents, we can build multiple generators and make them work together. Now, making them work together is kind of simple if we have a lot of data. Okay. If we have a lot of data, then actually you can train all of this mixer network as well as each of these lower level agent networks separately. Okay. So using a critic for each of them. I'm not showing the critic for these two networks here, but showing only one of the critics for one agent. And there is, of course, a critic for the mixer. The issue arises if we don't have a lot of data, or if the data is biased in some manner. So say for agent I0 here, we have limited data. Then how do we train this agent I0? This is the problem that we address in this paper. Can we train a good generative model of agent I0? Especially, can we use this interaction between the mixer and the agent I0 to help make a better generative model of agent I0? And that is what we answer in the affirmative here. We say that we can use the feedback from other dependent generative models to improve the generation of one of these lower level agent models. Okay. We also mathematically characterize that. This is a part I'll show briefly. I'll not get into the mathematical characterization. So the architecture is very simple. We have a critic for the mixer network, which provides feedback to the mixer generator. Okay, so that's all well and fine. But what if we use the feedback from this critic and use it for this low-level agent I0 generator, in addition to the feedback from its own critic? Will that be helpful? So the intuition is it will be helpful. Why? Because if the output of this generator of agent I0 is not good, it's not close to the true distribution, then because this mixer is a conditional distribution and one of its input is kind of not close to the true distribution, the output of the mixer will also not be close to its true distribution. And the critic will be able to catch that. We are assuming here that the other agents are well trained, meaning they produce output with true distribution. So this critic here will catch that there's something wrong with the output of the mixer's mixer network here. And that is caused only because this agent I0's output is kind of mismatched with the real world distribution. And hence this feedback that comes from the critic should help improve the output of agent I0. That's the intuition behind why the feedback from the critic can help. Okay. Now, this also has a mathematical characterization. This slide, I'm not going to read or even say anything about it. All I want to say is what I said on the previous slide, the intuition, it can actually be mathematically characterized in this theorem and lemma. I'm not going to read this because this is quite complicated. But what I'm going to show is our experimental result. So in our experiment, we do an experiment with time series generation, where there are time series of prices in 3 countries in Europe, which together influence the demand of electricity. And that is the relationship that's shown here. So these are the 3 agents, and this is demand is like the mixer network. So here we try low data setting. Okay, 2 types of low data. So this is 1 year worth of data. So we drop some data and we are left with 64 days of data for Spain and another setting of 124 data for Spain. So for one of the agents, we make it a low data problem. And we also bias it in some manner where we drop half of the data. So if we use a time series generator, so this COTGAN is a most recent time series generator from Europe 2020. It performs really good, but when the data becomes low or biased in some manner, then its results are not that good. Okay, so here I'm showing the result using something called an autocorrelation error. The lower it is, the better. So COTGAN by itself, if the data becomes less, then its results start suffering. But if we use the kind of feedback that I showed earlier from the mixer network to the prices in Spain, we can recover some of that. So that's what is shown in bold here. There are 2 variants of our approach. And we show in bold here that our approach gets a lower autocorrelation error, showing the improvement that you can achieve by getting the feedback from the mixer network. Okay, so this also has applications in transfer learning with that's an experiment I'm not showing here. So the main message here is that even when we have low data for some agents, we can still do a data-driven fine-grained simulation for multi-agent systems. And I think there are a lot more open problems in multi-agent simulations that are waiting to be addressed. So with that, that's a good opportunity for me to also talk a little bit about where I'm going. So I feel that there is a great synergy between AI, multi-agent systems, and problems in security and privacy. So physical security is, of course, a problem. I've shown some work of mine in addressing this. But this kind of adversarial problems also exist in the cybersecurity world. Okay, and that's one area that is amenable to game theoretic solutions. The only thing is the scale of cybersecurity problems is much bigger. So there's a scale problem there that needs to be addressed. There's some work that I'm already doing. For example, I'm looking at work on numerical instability attacks in neural networks. There's a work that I'm continuing from this paper. This paper is from 2019. This is a work on deception. But deception can be applied in many different manners, not just for learning, but also in planning and search and different AI components. As well as deception could not just be applied by the defender, but could by the adversary, but also by the defender to fool the adversary. So there's a lot of scope of rich work in coming up with deceptive strategies for players in a game. Okay, the next thing is simulations. So Complex systems like financial systems, as well as a complex security interaction in cybersecurity, if we can simulate this better, then maybe we can learn better defender strategies or better policy decisions. And that's something that I realized when I was doing some work on reinforcement learning, that simulators of human systems are not that great. And that's why I have proceeded to work on those topics. So right now I'm focusing on building a simulator for how humans can play a video game. So this is using data from many humans who play a toy video game. But the overall goal here is to build a reinforcement learning system uh, that can use such a simulator of how humans play in order to better help humans to learn how to play. Okay, because the simulator essentially captures how humans play a game. But for more real world application, these kind of training protocols can be used, can be designed by reinforcement learning for training of paramedics, for example, as well as firefighters and other different kind of training that are done in practice. Now, there's a potential work here on the simulation side, which is very important from a practical standpoint. The classic agent-based simulation that's done, it's a interpretable simulation, meaning we understand why an agent is making a certain decision. When, as I showed, if you replace an agent with a neural network, you lose that interpretability. We don't know why a neural network is producing a certain output. So bridging this gap between the interpretable agent-based simulation and interpretable neural network, I think is a very important thing to not just do simulation, but also understand why the simulation is resulting in a certain outcome. Of course, there are other things that can be studied. For example, large supply networks, if we can simulate them, then we can understand what are the points of disruption and how to make these large supply networks robust to such disruptions in practice, which could also be adversarial disruptions. Okay, so with that, the final thing that I want to, I didn't get time to talk about is this work on AI for social good. So this is a work I'm doing with Google Research India. This is where I'm looking at data quality issues in health data collection. So health data collection in parts of India are done on paper like this, and then they are entered into a database. So as you might imagine, there's a lot of scope of errors as well as mistakes, as well as some intentional mistakes that can happen. So how do we fix such errors? Okay. So first of all, we need some score to be even to able to quantify how good or bad the data is. So that's the one thing we are working on, is how to design such data quality scores. Now, once we have such data quality scores, how can we use it? So one way to use it is we can provide some interventions to the health workers and ask them to improve their data quality collection, focusing more on those health workers that have less good data. As well as we could use this data quality score to improve the downstream prediction task, because the downstream prediction task will not have good results if the data is bad. But if we have some idea of how bad the data is, then maybe we can use that in an intelligent manner to improve the downstream prediction task. This is some work currently in progress. That's what we are doing with a collaboration with the NGO in India. Okay, so that brings me to the end of my talk here. I will end with a quote, a modified quote actually. This is just emphasizing that the inherent nature of the world is as a multi-agent system. So it's important to consider the game and multi-agent aspect when we are solving real-world problems. Thank you.
Thank you very much, Dr. Sinha, for the very interesting talk. I think we have 10 minutes for potential questions that we have from the audience. Yeah, if you have any questions, feel free to ask Dr. Sinha.
Sure. I'm happy to take questions.
Everyone. Okay, so basically, I have questions regarding to your projections method to bound the output of the neurons using polytope, right?
Yes.
Yeah, a couple of years ago, basically, I also looked into this a problem, but you know, as you mentioned, the scalability is one of the problem very difficult to solve over there.
Yes.
I'm wondering, you know, like, is there any other approaches to bound the output of the neurons instead of using, like, you know, like polytope and projections layer?
Yeah, so I mean, one natural approach I think which is also commonly used is this polytopes are essentially constraints. Instead of putting them as constraints, you can pull up these constraints into the objective and put in a loss for violating the constraints. What that does is that's a soft enforcement of the constraint. It does not guarantee that the constraints will be met, but depending on the like the Lagrangian parameter that's used with that penalty function, it will ensure that the points that are produced will mostly lie inside the polytope. It does not guarantee that. So that's called the penalty method or the Lagrangian method. There are many different names for it. That's one thing that I know.
Yeah, there's other approaches. For example, like they use like a Leibniz bound to bound the output of the neurons as well. Like, you know, like you aware of that directions, and also there's another direction, basically very effective, like using theoretical bound of difference of privacy. Basically, you can still guarantee that the output will not be slip away a particular, you know, like a threshold there. So I'm wondering, like, because those approaches are very effective. So what do you see the difference between the two, and what are the advantages and you know, like the disadvantages of the other? Why you follow these directions?
So here, what we are trying to bound is the output at the last layer. We are not trying to get a Lipschitz network. We are, I'm not very well aware of the differential privacy work, but I'm assuming that some of the differential privacy guarantees are like probabilistic. So those things don't ensure a hard enforcement of the constraints if we apply like a probabilistic kind of guarantee. Because what I want here is that whatever output is produced should, with 100% probability, lie inside this polytope. And Lipschitz, like Lipschitz networks, also don't really guarantee that, because I mean, in a Lipschitz network, we are not really specifying the polytope as such. We are just saying that if the output is if the input is this close, then the output will be a certain amount close together. That's what the guarantee is.
Yeah, and under which conditions your bound will be broken?
So if we do this projection layer, under no conditions will the bound be broken. The output will always be inside this polytope.
Disregard the input. You mean disregard any
whatever the input is? Yes, whatever the input is.
Okay. Okay. Thank you. Yeah. Thank you. Yeah. Do we have any other questions, everyone, from the audience? No. So in that case, right? Maybe you know, like you have still have 5 minutes left. Probably you have. Do you have any interview after this talk?
Yes, I have one interview right after this talk.
Yeah, so maybe you have you can take 5 minutes break before the interview ends at noon. So so again, thank you very much everyone for joining the data science seminar series today. And if you have any questions, feel free to send you know, like Dr. Sinha an email. Okay. Yeah.
Thank you. Thank you. Thanks a lot.
Thank you, everyone. Thank you. Bye.
Bye.